Welcome back to ECE 441A, 541A. We are starting to run a little bit faster is, I guess, the take-home message from the announcements. Homework number 3 is due today. If you're interested in technical electives for spring or fall that are forthcoming, you can attend the Tech Elective and AMP. That's the Accelerated Master's Program. If you're interested in that, that's happening Wednesday at 5:30 in room 530. The reason I said we're starting to move a little bit more quickly is we have 2 more homework assignments that you will be held accountable for before exam number 2. And homework number 4 is due a week from today, and homework 5 is actually due the next class meeting, or Wednesday, the day before, or the lecture before, or the period before the exam. And actually there will be no period before the exam physically on campus. So if you're wanting to not walk over here on that Wednesday morning, you don't have to. There won't be any on-campus meeting on that Wednesday morning on the 17th. There will be an exam on Friday, and so you'll need to be paying attention to material that I might provide via D2L, video and notes, replacing the time that we will be missing that in-person hour or 50-minute session. Likewise, the week after the exam, you'll be rewarded with no class, and that's because of engineer's breakfast. That's the following Friday morning. We will not have class here. I still reserve the right to provide you with information or material, but I have yet to decide what will happen there. Lab 2, you will want to be familiar with that before the exam number 2. And I don't know if the stockroom is ready for you to sign up, but they should be. Hopefully they can start having you sign up. I haven't yet been able to upload all of the graded lab number 2s to D2L, but you'll need to communicate with your team member that submitted your exam number 2 or lab number 1, and work with them to see what you need to do. It's very important that you have the right G of S. It may be that prior to lab number 2, you want to simply re-execute lab number 1 to sort of verify that you do have the correct G of S. You'll need a good G of S to start continuing with lab number 2, which lab number 2 is worrying about changing the dynamic behavior of your system using feedback of position and velocity information. Those are the announcements. You have 2 more homework assignments beyond the one that's due today, prior to exam number 2, which is a week from Friday. What I want to do today is recap and complete design specifications. How do you decide where you want your dominant closed loop poles? And I'll be saying dominant a lot, and what does that mean? Maybe you have a 5th order system. 2 of those poles we will sort of assume are dominating the behavior, and the dominating poles are the ones closest to the origin. Those are the slowest ones, so they dominate. They last the longest. They dominate the response. That's what I'm meaning by dominant poles. So if you have more than a 2-pole system, in this class we'll agree with a wink and a nod that you'll simply focus on the complex poles that are closest to the origin. Hopefully we'll be able to stabilize the poles, and we want those dominant poles to be in certain locations determined by the design specifications. That's why it's important to understand what we're talking about today. We'll then go over the answers to the matching quiz, since that really was dealing with these design specifications. I was trying to get you thinking about poles and time response. Now that we're thinking that way, hopefully it makes a little bit more sense, or it's a little bit more clear how we can adjust the closed loop poles or the dominant poles to produce particular behavior, be that percent overshoot, settling time, peak time, etc. Then we will go through some examples dealing with settling time and this trade-off between speeding up the system, making the settling time shorter, and the accuracy, the steady state accuracy. Maybe you are okay to tolerate a certain error. Maybe you tell your plant to go to 6 centimeters and it actually goes to 5.4. But it gets there quickly. Maybe you're okay with that. Or maybe that's not okay and you need to be locked on. If you tell it to go to 6, it better go to 6. And we'll figure out what that means in terms of trade-offs relative to settling time and steady state error. Maybe you're okay to get there a little slower but have less error. That's what this trade-off is concerned with. Let's then recap what we worked on last time. And again, this is based on a pure two-pole system. Pure meaning there's no finite zeros. When you do have finite zeros, that kind of throws these specification connections off. So we have to learn to be a little bit more informed when we do have finite zeros in play, but at least this gets us started. When we have a pure two-pole system, at least we kind of know where to put those poles and why. And these specifications deal with 3 things: settling time, which we denote by a capital T sub s, peak time, which might be a capital T or a lowercase t sub p. It just depends, I guess, on what I decide to write in that instant. And percent overshoot, which a lot of times we will refer to as PO. The 2% settling time, and here I may be giving you a little bit more information just as background, just to remind ourselves of where this is coming from. Remember, we have this envelope of decay, and that's influenced by e to the minus sigma t. Or sigma is just the zeta damping ratio times the natural frequency omega sub n. Or sigma is related to the time constant as tau is equal to 1 over sigma. And sigma, we are negative sigma into the complex S-plane. Sigma is usually just an unsigned value. It's usually positive, and we're meaning that we're in the left half plane, that distance of sigma. That's the real distance into the left half plane. And this 2%, if you go to the grocery store and you ask for 1% or 2%, you're probably dealing with milk. Here, we're dealing with settling time. 1% or 2% means 1% is usually 5 time constants. That's the agreed on behavior. 2% in this textbook is 4 time constants, and this textbook usually talks about a 2% settling time. And that's because if you look at time, this envelope, decay envelope, being equal to 4 tau, then e to the minus 4 tau over tau is e to the minus 4, which numerically is 0.018, and that's roughly 2%. Your milk is probably a little bit more. I better make sure I'm still on. I tripped. Who knows if I hope I don't have to go back and re-record this. So, maybe you do. Maybe it would be better the second time through. Settling time, 2%. What does that correspond to? You now need to be looking or thinking about particular regions or sections in the complex S-plane. And sigma is defining really this vertical line that we want to be beyond or to the left. And I've now shaded that in the complex S-plane, and these triangles represent desired closed-loop poles that we are trying to achieve. So now when you say 2% settling time or settling time, you're really saying how far do my poles need to be, real part, into the left half plane. And that then can be associated with a vertical line. You draw that vertical line based on how big sigma is, and sigma is going to be determined by T sub s, your settling time, which is 4 over sigma. So if you want that less than some amount, then sigma is going to be bigger or whoops. So getting ahead of myself, I want you to help me. So if we want a faster system, if we want a shorter or smaller settling time, what does that mean in terms of sigma? Do we want sigma to be larger or smaller if we want a faster system? Fill in the blank. You have two options: larger or smaller. What do we want sigma to be? And here I'm assuming sigma is growing. If we make it bigger, then that vertical line is going further to the left. We'll put the negative on it. These poles, these triangles, are at minus sigma plus j omega sub d. And the other one, its conjugate, is at minus sigma minus j omega sub d. In this case, we're actually beyond sigma, but that's the notation that we're using. If that's the case, if we want to speed up our system, make the settling time smaller, what do we need to do with sigma? Move it closer to the imaginary axis, make it smaller, or move it further left and make sigma larger. So larger will be up, smaller will be down with your thumb. If you're sitting in front of a mirror, you can now check your work. At the count of 3, I want to see thumbs, either up or down. Up for large, down for small. 1, 2, 3. All right, everybody's getting this one. It should be larger, whether it was your thumb or forefinger, it's larger. Peak time. So now settling time was vertical. Peak time deals with the damped frequency omega sub d. And the background is in blue, but this is how we came up with time to peak is pi over omega sub d. We simply look at a step response, find the time when the first time when that step response reaches a maximum, or when dy dt is equal to 0. That's when sine of omega sub dt is equal to 0. And when does that? Well, that's when the argument of sine is pi, and there's how we obtain our time to peak as pi over omega sub d. What does that mean? Now we're dealing with a horizontal line. Now we want our complex poles to be beyond some omega sub d in order to achieve a certain peak time. So if we want a quicker start, what do we want to do with omega sub d? Make it larger or smaller? Now we have to go back and look at how it's related. Time to peak is pi over omega sub d. If we want time to peak smaller, now I hope it's clear what you need to do with omega sub d. Increase if we want a quicker start, or decrease omega sub d. If we want to get to our peak sooner, quicker, what do we do with omega sub d? Do we make it increase, go higher on the imaginary axis, or decrease it, make it lower on the imaginary axis? Remember, time to peak is pi over omega sub d. If we're trying to drive the left side down, what do we need to do with omega sub d? Increase or decrease? And I'm not even going to ask for a thumb. Just tell me. Increase. Is this making sense? Now we have a horizontal line for time to peak. We have a vertical line for settling time. What else do we have? Well, we can sort of bend that or move those lines on their side or tip them to achieve our percent overshoot specification. The percent overshoot specification is obtained here in blue by looking at the expression for the step response, the unit step response. And when we evaluate that unit step response expression at the peak time, or when t is equal to pi over omega sub d, a lot of things collapse and we just end up with 1 plus this interesting looking exponential, e to the minus zeta pi over the square root of 1 minus zeta squared. And if you are trying to frantically copy this down, don't forget that zeta is the square root of that mess in the bracket. We're raising it to the 1/2 power. And what's that mess inside? Well, that's just solving for zeta from this piece right there. That's where that expression for zeta comes from. If you had now a 20% overshoot, you would plug in 20 for PO. You have 20 divided by 100, or the argument of the natural log is 0.2. You take the natural log of that and square it, and you use that both in the numerator and the denominator. And do you remember what pi squared is roughly? It's about 10. So that's what you're comparing in the denominator with this natural log squared value. If somebody simply gives you a plot and they ask you to find the percent overshoot, the general percent overshoot expression is found by taking y peak minus y final divided by y final. And that was messed up on exam 1 a few times. People would get y peak in the denominator. That's not what you want. You want the percent overshoot based on where you finally reside with your constant output. That's what you're comparing your peak to. That's the percent overshoot, is y peak minus y fine over y fine. And really what you should be, I think, focusing on in all of these equations is this picture. Again, it's the S-plane, but now we are interested in this angle theta. And theta is going to change depending on the damping ratio. That's why it's called a damping ratio. If zeta is equal to 1, if your damping ratio is equal to 1, what's your angle theta? And that would be even more clear if I go down just a little bit more and remind us of the relationship between theta and zeta. Now we're starting to pull in some of all of your underlying math skills. We've already differentiated to worry about time to peak. And now what are we doing? Now we're doing some trig. We have to remember the cosine formula, which is adjacent over hypotenuse. The adjacent distance or length is sigma. That's zeta omega sub n for a pure two-pole system. And the hypotenuse is the natural frequency, the distance away from the origin. Sigma over omega sub n simplifies to zeta. Cosine of theta is equal to zeta. And this is what you need to be comfortable with, is associating zeta, the damping ratio, with the angle theta. Theta changes from 0 up to 90 as zeta changes from 1 to 0. As the damping ratio gets smaller, the angle gets bigger. I like to think of this when I was learning inequalities. Did you guys do this? Whoops. Probably didn't do it in a highlighter, so I won't either. But my second grade teacher actually did something like this. Where'd that come from? Anyway, we are now trying to think about this size. And so maybe you're thinking about a pie wedge or a size of pizza. If you want a better performing or less overshoot, you want that pizza size to be smaller. You want that angle to be closer to 0. If you want less overshoot, whoops, I'm probably already giving you the answer. Oh well, so be it. I want to make the point. I want you to be clear that as zeta gets closer to 1, what happens to that angle theta? What's theta do as zeta goes to 1? What happens to your piece of pie or your piece of pizza? It gets smaller in wedge size. That angle gets closer to 0. Zeta equaling 1 gives you a critically damped system, no overshoot. So a smaller percent overshoot corresponds to what for theta? If you want a smaller percent overshoot, what do you want theta to be? Closer to 90 or closer to 0? Smaller or larger? You want it to collapse that wedge. You want theta to be smaller, and what do you want zeta to be? When zeta is equal to 0, where are you with your pole? When zeta is equal to 0, when your damping ratio is 0, what does that say? Oh, I probably don't have any damping. What happens when you don't have any damping? You just sit there and shake, do you not? And you just continue to shake. You're on the imaginary axis. You're simply just whatever that omega n is, you're now at that frequency. That's your oscillating frequency when zeta is equal to 0. So if you want a smaller percent overshoot, you now have a theta that's smaller. What do you want zeta to be? Closer to 1, so you want this to be larger. And there's a nice, so we've been looking at this mess of a formula and also that it's highlighted in yellow, but if you plotted that picture or that highlighted expression as a function of zeta in MATLAB or with your calculator, you would find or generate figure 5.7. For a second order system, zeta now changes, and now what we will focus on is this curve that's going from 100% down to close to 0% as zeta goes from 0 to 1. That's the percent overshoot line. The other one we're not going to focus too much on. That's the peak time expression, but it's normalized and it's the right-hand side for the vertical axis. Don't worry about that one. We want figure 5.7 to focus on the left percent overshoot, vertical, and the zeta value. And how do we read this? What if somebody said, I want my closed loop poles to have a 30% overshoot? Then you would say, oh, I know now what your damping ratio needs to be. Your damping ratio now needs to be zeta equal to about 0.36. Or somebody says, no, I want less percent overshoot than that. I want a 5% overshoot. What's your zeta value? To get a 5% overshoot, you need a zeta of 0.7. And that's what I've done here below figure 5.7. I resketched it much worse than the actual curve, because now who knows if these are really valid. 0.6 and 0.7 look a little bit too far away, but the important point is to recall theta and zeta's relationship. If I say we have an angle that has a cosine of 0.7, what's that angle? Theta, the angle that corresponds to a value of 0.7, the inverse cosine of 0.7 is 45 degrees, roughly. It's 0.707, but 45 degrees is close enough. So if you want a percent overshoot of 5%, you want that pizza wedge to be at 45 degrees. And 45 degrees is a nice angle for your complex poles. Just saying. That corresponds to 5% overshoot. That's not much overshoot, and it gets you to your peak fairly quickly. What are some other common values? What if somebody said, oh, I want a percent overshoot of 10? Then go to figure 5.7 or plug in the zeta or the percent overshoot of 10 into that zeta equation, and you'll end up with something close to 0.6. On the exam, if you have figure 5.7, you can just quickly eyeball what your zeta needs to be. You don't have to spend time calculating the value for zeta if somebody gives you a percent overshoot. Or if you calculate a zeta, you can quickly read off from figure 5.7 what the percent overshoot is. Now, if you want a 10%, that angle grows. It's 53 degrees. If you wanted a 20% overshoot, now the angle is 63 degrees. Do you see how the wedge is getting bigger as the percent overshoot is getting larger? 50% overshoot, if I wanted to go to 1 and I had a zeta value of 0.22, or my angle was 78 degrees, I'm going to actually peak at 1.5. before I then return to my final value of 1. Maybe that's okay. Maybe I can go beyond my final value by 50% of that final value. Maybe that's okay. But all of these common values can be eyeballed from figure 5.7. What if we wanted to combine all three of those design specs? Now we get to some fun stuff, because we're not probably going to have one design spec at a time. We'll probably want to be doing multiple specifications at once. So how do we combine them? Well, first we need to draw our S-plane coordinates, or axes. And suppose now I want a given settling time. What's that correspond to? What kind of geometrical shape or line type, vertical, horizontal, or angled, does settling time invoke? If I want a particular settling time, what should I be thinking? I don't know, where's the drop form? No, you shouldn't be thinking drop form. What's the settling time line? Horizontal, vertical, or angled? What's the settling time telling you? Sigma, and sigma is going to be this vertical. So now if I wanted a smaller settling time, which way do I want that vertical line to be going? If I want a faster system, which is what this represents, do I want to move that vertical line to the left or to the right if I want a smaller settling time? Hopefully you're still just thinking about your weekend, is why I'm not getting much of a reaction. What about, I want to change colors. What about peak time? Omega sub d. That says we want to be above some, so here was omega sub d, and which direction do I want omega sub d, that vertical line, to be moving if I want a smaller peak time or a faster system? If I want a smaller peak time, which way do I want that horizontal line to go? Up. So now that one's going up for a smaller or a faster system. And now what if I want a percent overshoot specification? That's my pizza wedge. And what do I want if I want less percent overshoot? Which way does this is now my angle. Does that angle get bigger or smaller if I want less percent overshoot or smaller overshoot? So now this one, can I do this? Is that way if I want less percent overshoot. And do you see what happens when I intersect all three? I want to be to the left of the red line. I want to be above the blue line and below the green line. So that now I want my desired poles to reside in this shaded region. And do you see that there's not one correct answer? That's where a lot of times you get uncomfortable in this class, is you go, well, what's the correct answer? Well, there's an infinite number of correct answers that can be right there. They can move around, or you can locate those desired dominant poles anywhere inside that shaded region if those were your design specifications for a pure two-pole system. And now you see what you have to do if somebody changes or adjusts those design specs. If they want less overshoot, now that angle is going to start rotating down towards the real axis. If they're okay with a slower system, settling time-wise, now that vertical line can move closer to the imaginary axis. questions on design specifications and how you can adjust them. That should inform now our answers to the matching quiz from Friday. So here, we want to now think through what's happening relative to the time response versus the pole locations. Poles A or poles B. How are they similar? How are those two pairs of poles similar, or what characteristics do they share? In terms of what we've talked about today, sigma, omega sub d, and theta. What do these pairs of poles have the same? What's the same? Sigma, omega sub d, or theta? They have the same, they're on the same vertical line, aren't they? So that's the same sigma. And what does that mean? What should they enjoy or experience together? They should have the same percent overshoot, same peak time, same settling time. And do they? Do they settle at about the same time? And what is their real value? What is sigma? Can you see that? Sigma is 1. They're a distance of 1 into the complex left half plane. And what's settling time? That's 4 tau. That's 4 over sigma. Is our settling time? Is that when we get within a 2% tube? That looks pretty close, doesn't it? So that's consistent with what we would expect. All right, so we can't differentiate responses 1 and 2 from the settling time spec because they have the same real part, those poles. How do they differ? They differ a couple different ways, don't they? But one way is they definitely have a different omega sub d, do they not? And what does that mean? What should be different if their omega sub d's are different? Pardon? Peak time. So now their peak time, T sub p, is different. And time to peak is pi over omega sub d. And what do we have for this? System. Which one should peak sooner or have a smaller peak time, A or B? We're looking for a bigger omega sub d, and that's B, isn't it? Omega sub d now has a bigger peak time. Poles B have a larger omega sub d, which corresponds to a smaller time to peak. So which of these responses has a smaller peak time? The blue one, response 1. So now we're saying that B poles produce smaller T sub p, response 1. So now we're saying that we should have had a B1 and an A2. Is that what you guys, that's what you already knew. All right, let's go to one that was a little bit less clear. This one was about the same in terms of answers, but should it be? Now that we know a little bit more about design specifications, what would we expect to happen here? What's the same here in these two pairs of poles? What characteristic or property is the same? Omega sub d. So they probably, well, do they peak about the same? One may not even peak much because its zeta value is too big for much of a peak. So what's different between A and B? Sigma. So now we have T sub S is different, and how should we use that to our matching? Which one should be faster or have a shorter settling time? A is further into the left half plane, so A should go with which response? 1 or 2? So now it should have been the one that had the majority, not much of a majority, but it should have been A1, B2. Is that clear? What about the last one? What's sort of different on the responses? Is the settling time? Yeah, it's probably different, isn't it? Is the peak time? Yeah, it's probably different. What's maybe easier to think about in terms of behavior? That blue curve has a pretty good overshoot and the red curve does not. So which of those pole pairs might have more of an overshoot than the other one? And what gives it more of an overshoot? We want a bigger pizza wedge, don't we, for more overshoot. And which one corresponds to that? B. So now we're comparing B with response 1. So theta large implies percent overshoot large, which says now B is 1. So it should have been A2, B1 for the answer. And that's what you'd already concluded. Questions on that? Now that you have an understanding of vertical lines, horizontal lines, and angles, right, for design specifications and how those can be traded off or worked together. Let's now look at a 2% settling time example. And in particular, let's look at a closed loop configuration between Y and R. And now we want to say that our reference input, let's say, is a unit step. What does that look like in terms of a transformed expression? That's 1 over S. And let's say that now, for the first example, let's look at G of S equaling K sub 0 over tau sub 0 S plus 1. What is that G of S? If somebody gave you that G of S in an interview, how would you describe that G of S to your interviewer? What's the DC gain of that plant? Could you tell them? You could say, oh, this has a DC gain of? What's the DC gain of G? Why does it seem like I'm not connecting? Everybody changes their eye contact when I start asking questions. Hopefully if you're looking in a mirror, it's staring back at you, unlike the students in class. They turn their gaze down to their paper and act like they're frantically taking notes. What's the DC gain? K naught, K sub 0. It's when S is equal to 0. S equal to 0 is DC. The DC gain is K naught. What's the time constant? Tau naught. Where's the pole? Where's your open loop pole in this plant? G of S. The value of S that causes the denominator to vanish. Or S is reciprocally related to your time constant. S is minus 1 over tau sub 0. What if I now said if tau sub 0 is equal to 1 and K sub 0 is equal to 10, I want you to find the closed loop 2% settling time. Do you have enough information? And now I do want you frantically looking at your paper and working to try to find the settling time. What is the 2% settling time for this closed loop system when you now have a first order plant that's in a unity output feedback configuration? What is the 2% settling time? I didn't even hear a cheer. I thought I would hear a cheer at least, right? What's the closed loop transfer function? Cheer 2. Right, that's G over 1 plus G. H is equal to 1. So now we have K naught over tau naught S plus 1 over 1 plus K naught over tau naught S plus 1. We can find a common denominator in the denominator, and we end up with a transfer function of is that the closed loop transfer function? Now can you find the 2% settling time? Do you have a pure two-pole system? What do you have? One pole. Does that have a sigma? Is that so far into the left half plane? Yes. It has one time constant. And it's not tau naught, is it? Because we've put it in a closed loop configuration. But now if you find the pole of this for tau naught equal to 1, k naught equal to 10, where's your pole? Minus 11. That's reciprocally related to your time constant or your settling time. And I'll fill in the answer after class, but it's less than 1. And that's because we had a pretty good sized DC gain in a closed loop, in our open loop system, and we put it in a closed loop configuration. We'll pick up somewhere close to that next time.